Welcome. This is Earth 101, Chapter 8, and we'll be covering the outer planets today, and that means the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. So these are the big planets in our solar system. Give me 1 second here. All right. So, Chapter 8, here we go. So here they are, our big planets. And if you didn't notice, I got a haircut. Don't I look tight? Okay. Anyways, take a look at Jupiter. We've talked about the sizes before, but maybe just refresh your memory. A little tiny Earth right here. If you look, starting over here with Jupiter, the biggest planet in the solar system, it's about 11 Earths across, right? Saturn, the main body, about 9 Earths across, and Uranus and Neptune are both about 4 Earths across in size, right? So the scales of the planets, you want to have some size, idea in your brain about how big they are, but they are very, very big. It's also very, very dark out there. And why is it so dark? Well, because you're far away, right? The further you get from the sun, the lower the intensity of the sunlight will be, the brightness of the sun goes down. And it's actually something that you're supposed to understand. How does brightness work, right? Brightness works according to the formula that we've written before, and I want to go over that with you again, because the next chapter that we cover in the class, chapter 10, is all about stars and the sun. And it's those concepts that you need to understand for stars. So let's take a look at my little piece of paper here. And I have my formula for brightness, the brightness of the sun, for example. The brightness is the luminosity, which is the power of the sun. And we'll assume that's a constant, right? It's not changing. Divided by 4 pi, ignore that part, but this is the important part, d squared. D is the distance, right? So d is the distance. L is called the luminosity. And B is called the brightness, right? So this is an idea that the brightness, the larger the distance is, the smaller the brightness becomes, right? Because it's inversely proportional to the square of the distance, okay? So let's say that we started with Earth, right? What do we know about Earth? Well, it has a distance from the sun, which is 1 AU, right? That's the distance between the Earth and the sun. So if I had a sun and I kind of put an Earth over here and I say this distance, I'm not going to draw the full circle, but this distance is 1 AU, right? 1 AU. So where is Jupiter compared to this? Well, Jupiter is 5 AUs. I don't even think I can fit. I can't, right? I just have to pretend. Let's just pretend that I put out here Jupiter 5 AU from the sun. The scale is not quite right. I'm sorry about that. But how does that work? Well, at Earth, the brightness would be the luminosity of the sun. Actually, sometimes you put a little symbol like that, the luminosity of the sun. And then we divide it by 4 pi, and then we have 1 AU squared. Now, we're not going to do any math. I just want to write this out for you so that we can then compare. So when we go to Jupiter, right, the brightness will be the luminosity of the sun. That's the same, right? It hasn't changed. But this time, we're going to divide by 4 pi 5 AU squared. And so when you look at that, what's 1 times 1? The 1 times 1 is 1, right? But 5 times 5 is 25. So what you get is 1/25 times this thing, right? And this was the brightness when you were at the Earth, right? So the brightness at Earth and the brightness at Jupiter can be related by this very simple relationship. Because it's 5 times as far, it's 1/25 the brightness. So what about Saturn, right? This is kind of a nice, easy thing to do. Saturn has a distance of 10 AU, okay? So what happens to Saturn's brightness, right? Well, Saturn's brightness is going to be the luminosity of the sun divided by 4 pi times 10 AU squared. And what's 10 times 10? 10 times 10 is 100. So it's a 1/100th of what it is at the Earth, 1 AU. Okay, so that's a simple idea. So what's 1/25th in terms of a percent? If you put 100% and you divide by 25, you get 4%. And as a decimal, that's 0.04. What about 1/100th? Well, that would be 100% over 100. That would be 1% or 0.01. Okay, back to our slide. Back to our slide. So as you go further away from the sun, the brightness of the sunshine is getting lower and lower and lower, right? Getting dimmer out there. So this chart actually talks a little bit about that, right? So the relative brightness. So if Earth is 1, let's say 100%, right? Then what would it be at Jupiter? Well, Jupiter is 0.037, which is pretty close, by the way, because we're friends, to 0.04, 4%. And the reason is because Jupiter is just a little bit more than 5 AUs from the sun. But you can see Saturn right here is just what we said, 0.01, 1%. So Uranus is about 20 AUs from the sun, and Neptune is about 30 AUs from the sun. And you can think about that. That would be 1/400, 20 squared, and 1/900. Okay, so you can see this is pretty close to, this is 1/1000th, that makes sense. Okay, so 1 is the sun's angular diameter. So we've learned that the sun is about 1/2 degree as seen from Earth. That's 30 arc minutes. We put 32 as the real number. At Jupiter, it would only be 6. It would be 1/5 as big, right? About 1/5 as big. At Saturn, it would be half of that, right? So the sun is becoming a smaller and smaller, object in the sky. And when you're very far away, the sun becomes actually a star, right? And here, the author has introduced a really cool idea. Actually, it's cool, literally cool, right? The further you get from the sun, the less sunlight can do something to maintain your surface temperature. And so the objects out there further away from the sun are going to cool off more rapidly because they're getting less sunlight, even though sunlight is not a big contributor anyways. And so the equilibrium temperature is 255 Kelvin without an atmosphere, 124 Kelvin, 95, 59, 59, right? It's getting cooler and cooler. Why is it the same for these two? Not sure. Okay. So we talked before about the snow line, which is the location where little tiny ice crystals would have been able to form in the early formation of our solar system, in the protoplanetary nebula, protoplanetary disk, sorry. And it was where, ice could begin to form, water ice. And so if you go closer to the sun, you don't have as much water ice. When you go further from the sun, you have lots of water ice. And this is what we find, right? That past Jupiter, all of those planets, all of those bodies have ice in the planet or in their moons, right? It's very obvious. But we're gonna remind ourselves a couple of ideas. How do you build such a big planet, right? How do you get Jupiter and Saturn, Uranus, and Neptune? How do you build that? And the answer is you had to start with a core of terrestrial or icy material, but that core of material finally became large enough that its gravitational influence could sweep up the hydrogen and helium gas. So all of the outer planets have a lot of hydrogen and helium. Saturn and Jupiter have much, much more, right? They are big, massive planets with lots of hydrogen and helium. In fact, hydrogen and helium is the main component for Jupiter and Saturn, similar to our sun, right? But not necessarily the main component for Uranus and Neptune, the ice giants. Okay, so here is some data, and I want to make sure that you know that some of the numbers have updated. This book was written in 2013. The second edition is coming out in the fall, and you don't get to use it. Sorry about that, but I'm going to go ahead and update your numbers for you. Please update these numbers. These numbers have changed. So they're more updated. The rest of it is pretty good, right? So do you need to know everything? Not really. Actually, please don't write down everything. The thing to like just look at, let's take a look, right, at the mass, right? So Jupiter is about the equivalent of 318 Earths in mass, right? Saturn is 95. Uranus and Neptune are pretty small, 14 and a half and 17, right? Their radii, take a look, right, huge. We already said is about 7 times 70,000. How does that work? That's 11 times the size of the Earth. Is that quite right? Yeah, in kilometers, right? 66,400 radius times 11 makes, yeah, roughly something like that. Almost. And then, and again, 59, is that like 6 times 9 is 54, 64. Yeah, it's just about right. And then Uranus and Neptune are both about 4 times the size of the Earth. Their volume, again, is consistent. That's fine. The density is actually something that I want to mention. Okay, so this is not a hardcore science class. We are not doing a lot of calculations, but let's just talk about something important, right? Density. Density is this idea. It's not mass. It's not weight. It's density, right? What is it? It's mass divided by volume. It's how tightly packed is the matter being, compressed, right? So how much space does the matter take up? So some things have a high density and some things have a low density. Often we think of metals, a solid chunk of metals having a high density. And if you put it in water, what happens, right? It will sink like a rock. A rock has a pretty high density compared to water. On the other hand, a chunk of wood, right? A piece of dry wood, a driftwood, if you find it at the beach, you throw it in the waves and it doesn't sink, right? Because the density of the wood is less than the density of water. So actually, it turns out water is pretty important for us humans, right? We are mostly made of water. So let's learn the density of water. So would you please write down the density of water is 1,000 kilograms per meter cubed. That's the unit that we see right here. So now I can compare and I can ask a silly question. If I were to make a giant bathtub, right? And I took these become my bath toys, right? Jupiter is my new bath toy. And I bring it in the bathtub. Would it sink or would it float? Okay, and so as you look at the density, 1,330 is bigger than 1,000. So what do you say, sink or float? And you say sink, right? Because it's greater than 1,000. On the other hand, look at Saturn, 690. What would Saturn do? And the Saturn would float, right? So Saturn actually, if we had a big enough bathtub, it would float in water, right? Liquid water, right? The density, the average density of Saturn is the lowest of all of them, right? It's kind of interesting. Now, Uranus and Neptune, I have to be honest, I don't know a lot about them. And actually, nobody really does. We've never had a dedicated mission to go to either one. The only mission that flew past them is the Voyager mission. And it was just a flyby mission. So we didn't get a lot of information. We got some. It's very difficult to look at them with telescopes. But Hubble has looked at them and seen some interesting things like weather. We see seasons, for example. We'll talk more about that later. But they're really not as well understood. Okay, so, but if you look at the density, we have an average density. So Voyager did get this, by the way, an average density of about 1,300, which is very close to Jupiter. So sink or float, and you say sink. Of course, it's greater than 1,000. And Neptune, interestingly enough, has a much higher density, right? 1,760. It definitely would sink. Orbital radius, again, you should know these, but you don't have to know the exact numbers. 5, 10, 20, 30. That's what I memorize, and it's close enough, right? It gives you an idea. You can see it's not quite the same as the numbers here, but it's pretty close. The orbital period is kind of important. So would you please write down, Jupiter takes 12 years to go once around the sun. Saturn takes 29 years. Uranus 84, and Neptune 165. The further away you get from the sun, the longer it takes to make one orbit around the sun. Now, the rotation periods have been updated. So I would just want you to write down the latest information, but Jupiter certainly is the most rapidly rotating one of these bodies. So with a rotation period of only 9 hours and 56 minutes. Now, these are all pretty rapid. They're really big bodies, but they all rotate faster than the Earth does. Why are they rotating so fast, so quickly? What's going on? And I would hope that you might remember, I did a little demonstration for you when I'm sitting on a stool and I pull my weights in. What happens to my rotation speed? I rotate faster, right? And this is called conservation of angular momentum. So really, you want to understand that these are all rotating quickly because they formed from a cloud of gas and material and dust and particles that were rotating in some way. And when they coalesce together to form a whole, they must have rotated faster. Okay, so all of these are rotating pretty quickly. You could say about 10 hours for Jupiter, almost 11 hours for Saturn, 17 hours for Uranus, and 16 for Neptune. They are all very rapidly rotating. We have just updated, by the way, Saturn last year got 20 more. So this number jumped. It did have less, but now actually it has more. So the winner is Saturn with 82 moons. So please write down, Jupiter has 79, Saturn has 82, Uranus we still think has about 27, and Neptune only 13. Okay, so the last row is probably the most important thing, right? This is actually something that you really need to know. That Jupiter and Saturn are primarily made of hydrogen and helium, just like the sun, right? I keep telling you that because next chapter 10, we're skipping chapter 9, next chapter 10, we're going to talk about the sun and what's the sun made of? Hydrogen and helium. This is a really important idea for us, okay? And yeah, I mean, the answer is because everything in the universe is made from hydrogen and helium originally, okay? But Uranus and Neptune have some other stuff, right? They are significantly enhanced. So if you look right here, there's CH4 methane, NH3 ammonia, H2O water. So all of these three compounds are not going to be liquid. They're not going to be gases. They are solid. They are ices that are formed within the bodies, or that formed and then were captured by the bodies. Okay, so these are ices. Methane ice, ammonia ice, and water ice. Okay, so here we are. We're jumping to, this is a quick chapter, by the way, so please try to understand. There's so much information we could talk about, but we're gonna be very limited and just focus on some key ideas. So take a look at these cross sections. All of them may have a terrestrial core. Although if you listen to Phil very carefully, he said that it might not be there anymore. It might have been disintegrated and spread throughout the volume. We don't know. But anyways, but it probably was the reason why these started growing so effectively. Once the core was there, the core accretion model says that that core was able to gather the hydrogen and helium. So Jupiter was planet number 1, began gathering the first, right? And then Saturn and Uranus and Neptune came later. Okay. So what do you want to look for? So you got this core, which is a terrestrial planet-sized object. And then we have a very interesting green layer for Jupiter and Saturn. Remember, Jupiter and Saturn are called the gas giants. And this green layer is called liquid metallic hydrogen. This is pretty amazing, exotic, strange stuff, okay? So they have a core, a kind of a mantle, if you will, and then no crust, no solid surface, right? No solid surface. There is no solid surface. If you fall into Saturn or Jupiter, would you crash into the land? No. What would happen to you? Ooh, that's a really funny question. There's actually a website. Should I find it for you? Okay, I'll find it for you. What happens if you fall into Jupiter? And the answer is you die, right? Why would you do that? Don't do that. Don't kill yourself. Okay, but anyways, it turns out that the density of the planet does get larger the deeper you go inside. So your density is about the density of water. At some point, the planet has a density of about water. So you would fall until you got to that level. And then if you fell a little bit deeper, the density is actually greater and you would bob back up and stop sinking anymore. right? So you would just float there until you ran out of air and then you would die. Okay, so don't do it. Okay. Let's take a look at Uranus and Neptune. They're very different, right? They have a blue, oh, sorry, let me finish the story. So outside the green layer, we have this yellowish layer, and that is molecular hydrogen. So this is pretty normal hydrogen, much more normal. So you might call this the atmosphere of Jupiter and Saturn, right? Their atmosphere out here. So that's the mostly gas, but it might be high density gas, which means it behaves more like a liquid. Okay, so Uranus and Neptune are significantly different, right? Around their core, they have this blue layer, which is a mantle of ammonia, methane, and hydrogen. Okay, ammonia, methane, water is missing, and hydrogen, okay? And this is a mantle. Remember how the mantle of the Earth works? By convection. And this mantle, this blue layer, is also doing convection, but it's not silicate, it's not rocky material, it's icy material. Please keep that in mind. This is a big deal, right? Out here in the furthest part of our, further away from the sun, the rock is ice. The rock, right, what behaves like rock does on Earth is ice, ices. Okay, and they have a molecular hydrogen layer outside as well. Okay, so let's talk about these planets, right? So why actually, so back to this question, why do Jupiter and Saturn have the green stuff that Uranus and Neptune do not, right? They have hydrogen and helium, but they do not have metallic. This metallic hydrogen was hypothesized, but until a few years ago, it wasn't even possible for us to create it in the laboratory. The amount, okay, so why is it there, right? What is special about it? Why is it there? And the answer is pressure, right? Under pressure. Okay, so the hydrogen normally that you and I deal with is a gas, right? If you pressurize it, it becomes a liquid. But if you pressurize it even more, the atoms are like right on top of each other and so close together that they can share electrons. And they behave like a metal. This was just theoretical. It was just a mathematical model. But we had a problem, and I'll tell you about the problem in a few minutes. And the solution was to have liquid metallic hydrogen. So where does it exist? Well, in the core, but not all the way in the core, right? Outside of the terrestrial core, there's a layer of hydrogen that is densely packed enough under enough pressure that it becomes metallic. What do you notice about the size of the metallic hydrogen for Jupiter versus Saturn? You probably notice it's a lot more, right? Why would it be more for Jupiter and less for Saturn? Because the pressure is only sufficient for Saturn when you get deeper inside. But for Jupiter, you only have to go this far, right? Jupiter has more mass, more gravity, greater pressure. That greater pressure and density is what creates the metallic hydrogen. So why don't Uranus and Neptune have metallic hydrogen? And the answer is they just don't have enough gravity, which means they don't have enough mass, right? Their mass was not sufficient to generate this metallic hydrogen, okay? All right, so why do we need that? Why do we need the metallic hydrogen? That's actually gonna be coming up in just a second. And I think I got all the stuff for you. Yep. Okay. Okay, so here's the secret. We discovered that Jupiter and Saturn and Uranus and Neptune all have magnetic field. Now, Jupiter's magnetic field is the most significant magnetic field of all the planets. It is the strongest. It is a very powerful magnetic field. It dwarfs the Earth's magnetic field. Earth's magnetic field is just measly compared to this one. This is super powerful. In fact, it is number 2 in the solar system. There's only one body with a greater magnetic field than Jupiter. What would it be? The sun. That's right. The sun has a magnetic field too. We'll learn about that next week. But anyways, Jupiter's magnetic field is enormous. So how do you generate magnetic field? Do you remember? And how many people are saying the magnetic dynamo effect? Okay, good for you. So how do you create a magnetic field? By circulating electric charges, right? By circulating electricity, right? By generating a current. So you need to have a molten material or a liquid material that can conduct electricity. And in the case of Jupiter and Saturn, why is it that the inner core cannot be the source of a magnetic field? Why would the inner core not be a good candidate? And you might remember why the inner core of the Earth is also not a good candidate, because it is solid, right? And why is it solid? Because of pressure. The same thing that generates the hydrogen would make the innermost core completely solid. So any metal that is there is solid. It's not going to generate a magnetic field. Now, how do you get a magnetic field? We need a liquid, and that liquid is the metallic hydrogen. So Jupiter, an incredibly powerful magnetic field, and even though it's off just a little bit, you should notice that it's pretty close to the axis of rotation. This is what you get when you use the magnetic dynamo effect. So I like that. I'm so happy. I feel like I kind of get it. Yeah. And then Saturn's even better. Oh, wow. Saturn is even better. It's totally aligned with the magnetic field. And then look at Uranus and Neptune. I'm scratching my head. I'm not sure what's going on here. Remember, they don't have metallic hydrogen. They don't have metallic hydrogen, and their magnetic fields are a little bit wacky. They are a little bit wacky. What's going on? What is going on? Okay, so I don't have a good answer. I will talk about it in just a few minutes, but I don't really know for sure, and nobody really does. But clearly, there's something a little bit different happening in Uranus and Neptune, which means that the axis of rotation, this black line, and the magnetic poles, the red line, do not line up. They don't line up at all. They are just wacky, okay? All right, so one of the things we notice, a fast rotation rate, what happens when you rotate a spherical ball of gas really quickly? Well, what happens is it flattens, right? It's not a pancake because it's not going fast enough to be a pancake, but it makes the distance between the poles smaller than the distance around the equator or across the equator, like that. And so they have incredibly rapid rotation rates and very high speed winds in their atmosphere, blah, blah, blah. Okay, so let's take a look. So look at Jupiter. Oh my gosh, it's so beautiful. And you might recognize the great red spot. Now, actually, we really want to be aware that Galileo was probably the first person to see that red spot and actually watched it. And it has been watched ever since, and it has been there ever since. So we're talking about, you know, something that has existed as long as telescopes have looked up at the sky. And for that time, this red spot has been there. What is the red spot? You guys know, it is a storm, right? It's like a giant cyclone. It's called an anticyclonic rotation, blah, blah, blah. But anyways, it is a storm that has been going on for hundreds of years. How is that possible? Can you imagine, right? A tornado or hurricane over your town for hundreds of years. It's like, why would you live there? But anyways, there's a reason, right? Storms represent energy, right? Energy. So energy is being pumped into the storm. What kind of energy? Well, the easy answer is thermal energy. So if you remember, the only way that a body can cool off is to radiate the energy away from the body into space, right? That's the only way. But to get that energy to the surface, right, from inside the core where it's concentrated, right, where it's hottest, out to the edge, right, it will be different processes. Okay, so it turns out that energy is escaping from Jupiter and Saturn from the day it was born. They're still cooling off, right? They are so large that they are taking a very long time to cool off. So they radiate, you want to write that down, much more energy than they take in, much, much more. Okay, this is an important idea. So somehow, as the energy is trying to escape, some of that energy goes into keeping the storm going. And we see other little things like that. Now, the other thing is to notice that the storm is in between two of these layers right here. So we're going to be learning some names, right? We have these dark layers and the light layers, okay? And they have names. So the dark layers are called the belts, and the light layers are called the zones, and they alternate, right? And you're like, why do they alternate? There's some kind of a pattern here. I see a pattern. And by the way, please look at the latest images of Jupiter from the Juno mission. They're just beautiful for no other reason. Just look at them and just be like, wow, it's like looking at an amazing sunset, but they're just incredible, or like works of art, except they're just nature. Nature creates these incredible storm patterns and wisps and just really cool, beautiful turbulence and all kinds of things. Very rapid rotation. So anyways, yeah. So because it's in between, that may be one of the ways that it has survived so long. The energy is pumping into the storm, keeping it going. So what is the composition of Jupiter? About 75% hydrogen, 25% helium, blah, blah, blah. You don't need to know that. Yeah, you don't need to know that. Okay, maybe the core is 30,000 Kelvin. That's quite a bit hotter than 6,000 Kelvin, which is the core temperature of the Earth. But remember that the core of Jupiter must be completely solid. And then outside the core, the metallic hydrogen is what is going to generate the magnetic field. Now, how do we actually know that Jupiter has such a powerful magnetic field? That's a really good question. We'll get back to that in just a second. Okay, so when we look at these layers on Jupiter, we do see clouds. And the clouds on Jupiter are made from a few different things. There is water vapor. There's actually water vapor clouds. There's hydrogen sulfide, and there's ammonia. So all of these clouds are going to be present on Jupiter. And so the upper part of the atmosphere is hydrogen. Okay, so the upper layers of clouds are ammonia droplets. The middle layer is hydrogen sulfide, and the lower layer is water. Okay, and there's some complex compounds too. Okay, but here is a picture, right? So the belts and zones on Jupiter. If you look at your book, this is the picture. And unfortunately, it's completely wrong. Sorry about that. But the direction of the flow is wrong. This is convection, right? So this is convection. So one more time, this is the wrong direction. The arrows are exactly backwards, but it's convection, okay? So the right answer is this, right? So that the zones are rising clouds, right? Rising material, which means what? The hot material is lower density and rises to the top of the atmosphere, cools, and then falls back down in the belt areas, okay? So actually, this is kind of a cool thing. First of all, to understand that the belts that you see, belts and zones on Jupiter, are also found on Saturn, and they're probably also on Uranus and Neptune. They're just not very visible. But Jupiter's got these beautiful stripes that you can see. These are convection. This is heat energy trying to escape from inside the body, right? So that's what's going on, right? It's heat energy that has to circulate, and that's the most efficient mechanism the planet has found, okay? Now, a few years ago, a student of mine heard me say that this is the hot material rising, and this is the cool material descending. And he immediately went to the internet and looked up an infrared picture of Jupiter. And he said to me, Dr. Kelly, you lied to me. you told me that the white areas are the hot material rising, and the dark material falling is the belts are the falling material, the cooler falling material. And I have to admit, that's what was showing up, that the belts looked hotter than the zones. And I was pretty flummoxed. I was scratching my head again, right? And it turns out it's perfect. It works beautifully, because what's happening is that at the top of the white layers, the zones, you have clouds that are forming. So you're looking at the outermost layer. And how does it work? Remember that the gas rises and cools and then falls down, right? So you're looking at the very highest part of the zone, which is cool. And then right next door, those clouds aren't present. So you're looking deeper into the planet to where it's warmer. And so the infrared picture actually makes perfect sense. It's just because the clouds are not there. But in fact, it's exactly what I just told you. This is the rising material is light in color, and the dark material is falling. Okay, so this is what's going on. Okay, so convection, right? We're talking about convection. So here is the idea that we have this incredibly powerful magnetic field. Actually, it's so powerful, right, that it traps a lot of charged particles. And there's actually a really dangerous amount of these particles in orbit around, around Jupiter. And it's one of the reasons why it would be kind of dangerous to send people there right now. We don't have the technology to shield them yet. But anyways, how do we know that Jupiter has such a powerful magnetic field? And the answer is because we see auroras 24 hours, 7 days a week, all the time, right? These are auroras on Jupiter, but not just any auroras. These are X-ray auroras. And if you have been paying attention, remember X-rays are one of the highest frequencies electromagnetic radiation, right? They're just gamma rays are the only thing that's higher than that. And so this is such a powerful magnetic field that the charged particles that are spinning around, following the magnetic field will come out and energize the atmosphere and produce X-rays. So 24/7 X-rays from Jupiter from such a powerful magnetic field. Isn't that crazy? So it turns out, I don't have pictures for them right now, but it turns out that of the Galilean moons, 3 of them also have auroras. So as soon as you hear auroras, what do you say? They have magnetic fields. And I'll tell you that the only one that doesn't, of the 4 Galilean moons, the only one that doesn't have auroras is Io or Io, right? That's the only one that doesn't. So anyways, we'll come back to that in just a minute. So the mission that is at Jupiter right now is called Juno. If you follow this link, you can go to the Juno mission page and look at some pictures and learn more. Again, I'm not going to be testing you on this, but except for the name, you need to know the mission Juno that is there right now. But what are the 4 main goals? Determine how much water is in Jupiter's atmosphere, which is going to be a check on our current hypothesis for planetary formation, and look deeper into Jupiter's atmosphere to measure the composition, temperature, cloud motions, and other properties. And they've been doing this. They've been watching the flow and seeing the movement of the convective flows underneath the surface atmosphere. Map Jupiter's magnetic and gravity fields, revealing the planet's deep structure. So is there anything left of the terrestrial body, right? If that's in there, by the way, then they'll be able to see it with these gravitational maps. And the magnetic field, I think, is really trying to understand how that metallic hydrogen is really functioning. And then explore and study Jupiter's magnetosphere near the planet's poles, especially the auroras, Jupiter's northern and southern lights, provide new insights into about how the planet's enormous magnetic force field affects its atmosphere. So it's just a significant part of Jupiter's being, right? This magnetic field. Saturn also has a very powerful one, number 3, right? So Sun, Jupiter, Saturn in order are the powerful magnetic fields in our solar system. Okay, so here are the 4 moons that you have to know about. You have to know the 4 Galilean moons. And remember, Ganymede is the largest in the solar system. I updated this for you, right? Jupiter has 79 moons. This is 2020 latest information. So which of these 3 moons has a magnetic field? And the reason we know is because of auroras. We know that Ganymede, Europa, and now Callisto, right? These 3 all have auroras. So you're stopping, you're saying, okay, they have auroras, Sean. What do I care? Well, you need to care because as soon as you hear aurora, you know that they have magnetic field. As soon as you hear magnetic field, you have to come up with a mechanism. How do they generate their magnetic field? And the answer is, well, metallic hydrogen. No, that doesn't work. These are made of rock and ice. And so that's not going to be present. So what do you need? You need metal of some kind, right? Well, guess what? They're too small. They should be cool, right? They're not going to have large metallic cores. So now you should scratch your head a little bit more and say, okay, Sean, how do you generate a magnetic field? And the answer is salty water. Yes, I'm not kidding. The ions in water, it turns out, must be circulating in these bodies. So each of these three, Ganymede, Callisto, and Europa, all have subsurface oceans. Yes, I'm not kidding. It's amazing, right? And these oceans are generated at least a weak magnetic field, enough to generate auroras, okay? So that's the explanation. Why do Ganymede, Callisto, and Europa have magnetic fields? Because they have ions circulating in their water oceans, H2O water oceans. Okay, so let's take a look at Callisto. Why Callisto? Why Callisto first? I don't know. Because it's mostly boring. And actually, until I heard about the magnetic field, I wasn't that excited either because it's mostly dead, right? How do I know that? Look at all the craters. The craters tell me that the surface is old or young. And you say old, right? It's very dark, low albedo. The low albedo comes from lots of dust that's been deposited on the surface from year after year, eon after eon of collisions and then ejecta spraying across the surface. But if you look, you'll notice that there's some light patches too. That's fresh. That's ice, right? And so the story for the outer planets, especially the outer planets, is when we see dark, we know it's old and dusty, right? Made of dust particles, metal or silicate, right? And then when we see, or carbonate, or carbon. And then when we see the light color, the high albedo, the highly reflective, we know that that's fresh ice. That's from craters, new craters that have formed. So the fact is that these have ice in them, right? There's ice here, not a lot. It's not completely ice, but there is a lot, sorry. There's not a lot at the surface. There's only a little bit in patches, but that's kind of interesting. There's more features, but that's all I really need you to know. The largest, sorry, not the largest moon, the furthest from Jupiter, Callisto, does have a subsurface ocean. Ganymede is the largest, and this one is a little strange, right? It has some darker areas, which look a lot like Mare to me, right? Mare on our moon. It has some craters, right? Which tell me that it has some surface, got some rays right here, which are fresh craters, and it has some light colored stuff, which is icy. And one more time, does it have a subsurface ocean? Yes, it does. It has a subsurface ocean that is generating a magnetic field. So now this one's a little bit closer. I hope you will watch, please watch the little video on tidal forces and the Roche limit. But Ganymede is being heated somewhat by Jupiter in its orbit. And it has a really kind of interesting orbit. We'll talk about that in just a few minutes. But actually its orbital period is 4 times as long as Eo's, I think. I'm going to check on that. I will check on that. Let's check that right now. Hold on. Let's just check that. Fact check. Fact check. Hold on. This is a fact check on the orbital periods of the Galilean moons, right? Hold on. Orbital. They have a very interesting relationship. Periods of the Galilean moons. Fact check. I meant to check this. Okay. So JPL, we like that. JPL. Okay, here we go. EO radius. Okay, orbital period. 1.7, 3.5. Anybody notice something? Europa is just twice as long as EO. And how about 3.557? That's twice as long as this. So it goes 1, 2, 4. Now this one doesn't quite work. Okay, so that's my fact check. So EO turns out to have an interesting effect. Actually, it just becomes a foundation for what we're going to talk about. But anyways, Ganymede, we said, is 4 times as long to orbit Jupiter as EO does. Okay. All right. It does have some interesting features. Don't worry too much about some grooves. Actually, those are kind of interesting, but again, I'm not going to worry about it. It is not known if Ganymede is geologically inactive. So I think Juno will be looking for that. I don't know how much of the mission is dedicated to that, but I'm sure it will take a look. Okay, here we go. Europa, super, super amazing. Europa. You'll notice that it has some interesting colors, colorations. It is very high albedo. It reflects a lot of light, which indicates ice. And actually, if you look, there's a bunch of holes right here. Those look like craters, but listen carefully. There are no craters on Europa, none, zero. And what about those holes, right? And so you listen, this is a new thing, an exciting, fun thing. Those are cryovolcanoes. They erupt water, right? Those are water volcanoes. They don't erupt magma, lava. They erupt with water. They squirt water out, okay? The subsurface ocean. So Europa has no craters at all. And interestingly enough, when you look over here, this interesting crystalline pattern, if you look at the Earth, does anybody know where you might find something like this? And the answer is near the Arctic Circle. You find ice flows that look just like this. We think that that's what's going on. So Europa is an icy world, completely covered with ice, but underneath that ice is a liquid ocean. Now there is a very exciting, there's a planning stage right now. NASA is planning a mission to Europa, and this is amazing, right? It will send a submarine to Europa. It'll land down on the surface and then melt a hole down into the ice. I think it's pretty deep. I don't want to say 20 miles, but I think it's something like that. And leave behind a big long wire antenna, and then go underneath the ice and then zoom around and look for things, right? Look for whatever is underneath the ice. That would be pretty cool. They're planning that mission right now. Okay, so Europa is one of my favorites. Very cool. There's a possibility that life is on Europa today, right? It has the right kind of conditions under the ice, low radiation, nice temperature, liquid water. Okay, so Europa, why does Europa have such a lot of water? It turns out because it's closer to Jupiter. Jupiter's tidal force is stretching it and heating it enough to keep that ocean molten, right? To keep it liquid. So very young surface, no craters, right? Candidate for life, okay. And our last one is Io. Oh, beautiful little Io, a little pizza planet, sometimes people call it. It is the most geologically active body in the solar system. And this body has volcanoes all over it. I've heard that it has 300 volcanoes, but maybe not 300 active volcanoes, but it has active volcanoes literally all the time. So anyways, how is that possible? Well, this is a little body. It's smaller than our moon. It should have cooled off a long time ago, but it is really close to Jupiter. And Jupiter is stretching it with the tidal forces. So it is the closest one. And we saw that it orbits in 1.7 Earth days, right? Is that right? 1.7 Earth days. And that's right, 1.7. And as a result of that, so it's very frequent, right? It's being stretched the most. Europa has twice that period, and Ganymede has 4 times that period. So they are in resonance with each other, and they are kind of reinforcing each other. And actually, you'll hear in one of those video clips, they have a more elliptical orbit, which actually generates even more heat. Now, Callisto is much further out, so it's not affected as much by the tidal heating. But anyways, Io, tidal heating gives it that incredible volcanic activity. Okay, let's move on. And here we see the best picture that Galileo ever had. Galileo actually could not see the rings as separate from the body. So Galileo said Saturn had ears, right? He imagined it was like ears. And it was Christian Huygens who developed a better telescope, actually, that was finally able to resolve the rings and see the space between the planets and the rings. And that's a pretty exciting thing. So this, by the way, its nickname is the Lord of the Rings. It is a really incredible planet to see with a telescope. Later this summer, hopefully there will be an opportunity. If not, I'm hopefully doing a virtual star party where I'll show you through a real telescope what Saturn looks like. It's up about 11 now. And by the end of the month, it'll be up by 10. So you don't even have to stay up that late. But Jupiter and Saturn are two incredible planets to look at, really wonderful. So just to let you know, this is one of the most exciting missions in my life. I honestly can't tell you a more exciting mission than the Cassini mission. This is truly a testament to humanity's possibilities. And so you should all feel proud. And I want you to please watch that video about the Huygens landing. It is just so important. If we were in class together, I would savor it with you, but I'm not going to do it in this lecture. I'm just going to tell you to please watch it. It's so beautiful. But they launched it in 1997, and in 2004 finally went into orbit around Saturn. And then one of the first things it did is dropped a probe onto the largest moon of Saturn called Titan. You need to know the name Titan. Okay? You don't have to know a lot of moons of Saturn because Saturn has 82. I'm just going to learn one, Titan. So it had a nominal mission, which means it was supposed to last at least 4 years, and then it kept going, and it went on for 13 years. Actually, you need to know a couple moons, sorry. You need to know 2 moons around Saturn, Titan, and the second one, Enceladus, which is another watery world. Should we look at this? Oh man, okay, I'm gonna look at this. Let's look at this just for fun. Hold on, let me switch to the animation. Okay, I didn't think I was gonna do any of this, but it's just, you gotta see some of this. This is real footage. Okay, well, that is quite beautiful. I hope you'll go and watch that again on your own. It's really amazing. Okay, so this is the Lord of the Rings. Let's see, it can fit 764 Earths. You don't have to know that. You do need to know that it has the lowest density, and it does have that metallic hydrogen, like we said. So does it have a magnetic field? Of course it does. It's got a magnetic field. Very fast. We said actually it's close to 11 hours now, right? And because of that rotation, Saturn, for some reason, is a little more oblate than the other planets are. And I think we can skip this other than that. Okay. There is kind of an interesting thing. Remember, it takes 29 years to orbit the sun. And so as we watch over time, the rings don't look the same as we see Saturn, right? The rings are pointed, sometimes very visible, and other times we can actually see edge on, and they seem to disappear for a little while. So interestingly enough, because Saturn was so big, right, it gathered all this material together. It has a lot of heat energy as a result from converting the gravitational potential energy into kinetic, into heat energy. And it's actually emitting more than 2.5 times what it is receiving from the sun. So all of this infrared, mainly infrared energy that's escaping from Saturn, actually should be causing the ice in the rings to sublimate. So the rings shouldn't be there. And so this is an important idea. The rings of Saturn were not born with Saturn. They are definitely not. So in fact, sad news, we have seen that the rings are going away, right? The rings of Saturn are going away. They will not be here forever. And that's very sad, right? Except I have some good news too, okay? So anyways, I don't know what else. Helium rain, oh, that's kind of cool. Yeah, don't worry too much about that either. But this is actually from different points in the orbit, right? So we see Saturn taking almost 30 years, 29 years to go once around. At different times, we will see different sides of Saturn as a result. We can see it, right, almost edge on, or we can see the rings. Right now, the rings are pretty nice. They're pretty visible, actually. Pretty nice, actually. In fact, so what would it be? So this is more like this. I think it's going to be more like this, right? So actually, maybe more like this now that I think about it. But anyways, that's important. So again, like Jupiter, we've got the hydrogen on the top. We've got methane, ammonia, hydrogen sulfide, and water. These were similar to Jupiter, and incredibly fast winds. That's true. You don't have to worry too much about altitude or density or temperature or anything like that. But again, clouds of ammonia, hydrogen sulfide, water, same story as before. Does it have belts and zones? And the answer is yes, but they're much fainter. They're not as strong as in Jupiter. So we don't see that. I actually left something out, something kind of important. Both Jupiter and Saturn, even though the sunlight is weak, the question is, does it do anything at all? And the answer is yes, it does, right? Even though it's weak, the sunlight can do something. And what it can do is it can do a little bit of chemistry in the upper atmosphere. So because of the energy of the sunlight, there is actually some interesting things that happen. Complex molecules can be created with this energy. So it's not a lot of energy, but it's enough for a little bit of chemistry to take place. So more complicated molecules can form as a result of that. And they become like pollution almost, like smog, like haze, and we're going to talk more about that. But we do see that in other places as well. There's an interesting, very funny, and again, it seems to be just because of a coincidence, because of its fast rotation rate. It turns out that we see this hexagon storm in the North Pole of Saturn, and you'll see it if you watch the video. Some of the video clips that I posted, at least one, you will see that. And we have seen other storms as well, kind of like the big red spot. There's actually a big dark spot on Saturn, although it's not quite as significant, and it certainly hasn't been around as long. Anyways, yeah, don't need to know much about this either. But you do need to know about 2 of the moons. Okay, so it has 82 moons right now. It actually has some strange moons too. So the regular satellites go in the same direction around Saturn as its rotational direction, which means they probably were born with Saturn. But it also has some that are very weird, right? They're highly inclined, highly elliptical, or even going backwards. And these are captured objects, right? So we can see that there's a difference. There's some that were formed with Saturn and some that came much, afterwards and were captured. But this is incredible. This is the most important moon in our solar system in some sense because it has an atmosphere. Well, okay, it's kind of cool. Titan is a moon with an atmosphere. Okay, you want to make sure you know that. And then the other moon right here is called Enceladus. And if you look at it, you might say that, and this is actually an easy thing to be confused. It looks a lot like Europa, and it even starts with the letter E, right? Remember, Europa is the water world of Jupiter. This is Enceladus, and this is a water world as well. So very, very similar story. And again, those circles that you see are not craters. What could they be? And the answer is cryovolcanoes. They're jetting water. And we'll talk more about that in a little bit, okay? Let's start with Titan. Titan is amazing. It is a world which is complex. It has an atmosphere, so it has weather. It has mountains, it has lakes, it has rivers and river deltas. It is amazing. We've seen the shine of the sunlight reflecting off the lakes, okay? The Titan mission was called Huygens. The probe dropped down through the atmosphere. Please watch the video. It took 2 hours for it to fall through the atmosphere on a parachute, and it was doing radar imagery the whole way down. It is amazing. Okay, so what is going on? It has mountains, it has lakes, it has rivers, it has rain, right? It has a cycle, but it's not the water cycle that we have on Earth. Why? Because it's just too cold. Okay, so a couple of things to note. It is alive and it has weather. It's changing. I don't know about plate tectonics and all that stuff. I don't think so, but it definitely has mountains. The mountains on Titan and the rocks on Titan, and please watch the video. Please, please, please. You'll see these boulders that are rounded from erosion. Oh my gosh, it's beautiful. They look just like boulders on Earth, but those boulders on Titan are made of, just like the mountains, made of water ice. Water ice is the mountains on Titan, and the boulders and the rocks, right? So, and so what is the liquid stuff? What is the rain, the rivers, the lakes? What is it made of? And the answer is hydrocarbons, either methane or ethane or possibly butane and propane, but mainly methane. Methane is a liquid on the surface, and then it evaporates, turns into droplets, falls as rain, and erodes the mountains, right? Exactly like it does on Earth. Beautiful winding rivers, river deltas. Oh, it's incredible. So we see this incredibly rich structure and weather like we didn't imagine. So the one question that I have for you is, this moon has an atmosphere. How is that possible? Our moon doesn't have an atmosphere. Our moon is bigger than this moon. So why would it be? And the answer is two answers, right? One, that it is a pretty big moon, right? So it has a substantial gravity, but our moon would be okay in that respect too, right? And the second is because it's so cold. The gas molecules never get a lot of energy, and therefore they can never escape from the planetary gravity. They don't have the escape velocity, so they're trapped there. And so we see a nitrogen atmosphere and a haze of hydrocarbons. Okay. Again, you don't have to know too much about that, but it's just incredible. And I hope you'll watch the videos and just be amazed. Okay, Enceladus is really critical because we see something very interesting. So Enceladus has these cryovolcanoes, and they're actually not just like holes, there's whole themes, right, where water is squirting out at extremely high velocity. In fact, so fast that it's escaping from Enceladus. So Enceladus water is escaping from the body and going into orbit around Saturn. And the little droplets of water are crystallizing and forming a ring, the E ring. And the E ring, by the way, is really fuzzy. So when we talk about the rings of Saturn, this is a different ring. It's much further away from the planet than the rings that you and I will normally think of. We can't see the E ring except with a very powerful telescope and with the being up close with the Cassini mission. So Enceladus could possibly be a place for life. A little tiny story. I don't want to tell you any. I want to tell you too many stories. But the Cassini mission, and in the very beginning, as soon as they got there, the scientists said to the engineers, can you fly through one of the jets on Enceladus? We want to see what it's made of. And the engineer said, not a chance. Are you kidding? We just got here. If we fly through those streams, it could destroy the instrumentation and then we'd be done and we wouldn't have any. But by the end of the 12th year, the scientist said, hey, can you fly through Enceladus streams? And then sure, why not? Well, if it screws up, we're already at the end of the life. So at the very, last year of its mission, it flew right through 30 miles. Oh my gosh, 30 miles above the surface of Enceladus. It flew right through an erupting geyser, a cryovolcano, and tasted the water and found out that it has hydrocarbons in it. So it's salty and it has hydrocarbons, it has organic compounds in it. Oh my gosh, this is really exciting. But anyways, so we don't know. There's a lot of information still to find out, but it's really exciting. This place could harbor life right now. All right, let's talk about those rings. Those rings are incredible. They're huge, right? They go from a distance of 7,000 kilometers out to 80,000 kilometers from the edge of the planet. They are enormous. Now, outside of them, you see this ring? That's the E ring, right? And right in the middle of the E ring is Enceladus. These rings are different. There's an F ring here too, okay? So these rings are different from this ring and this ring. There's something interesting about them. And so, first of all, we want to talk about why we can see them so well. And the answer is because they have a high albedo, right? And that means they are mostly made of ice, right? Water ice, mainly water ice, okay? Although I imagine there's even other ices, but they are incredibly big, right? So we're talking 160,000 kilometers across and 10 meters thick. This thickness right here, it is the sharpest thing that you can imagine. We have never seen anything like this in the entire universe. I mean, there must be more stuff like this, but it is truly amazing. These rings, as I mentioned to you, should not be here actually. Saturn is giving off so much infrared radiation, these rings should have sublimated away. But the reason they're there is because they weren't born with Saturn. They came afterwards, okay? So we do want to talk more about that. The rings are actually made up of thousands and maybe even millions of little ringlets. And some of the rings are very old and made of dark, dusty particles, but other rings are actually young, okay, relatively young, maybe as maybe only 1 million years old, okay? There are some different kinds of rings. So the inner rings, I do want to make sure you understand there's a kind of an important idea, and I did post a video. I'm going to go ahead and write just for a second. I want to talk to you about the main rings, okay? So the main rings, it turns out, are kind of close to the planet. So there's an idea that Saturn has got its rings, and the main rings are within this distance right here. And it's about 2.4 radiuses, right? So you go, actually, I didn't really draw this very well. Let me make it a little bigger. So 1 radius, 2 radius, 2.4, right? So the main rings are within this distance right here. And this is called the Roche limit. And it's kind of an important idea. And it turns out that we can't get a moon to form inside that Roche limit because why? Well, if you try to put a moon here, what happens? Well, the force of gravity from Saturn is going to pull it apart. Remember, that's called the tidal force. The tidal force is too strong. And so it turns out that we actually think that if you took an object like a comet or an asteroid and you brought it a little bit too close to Saturn, that it would actually rip it apart and perhaps form a ring. That one of those video clips that I posted for you shows you a nice animation of this. And so this could be where the rings come from. So what's really exciting is Uranus and Neptune and Jupiter all have rings as well. I forgot to mention Jupiter's rings. Sorry about that. I'll come back to that. But the rings are really hard to see because they're mainly made of dark, low albedo particles. And Saturns are beautiful, bright, icy rings. Okay. So the main rings are inside of this thing called the Roche limit. Outside of the Roche limit, we have two more rings, the F, the E, and the F ring. Okay. And the F ring is kind of special because it has these two moons that are on either side of it. And so this F ring is special because it has shepherd moons. These shepherd moons seem to keep the ring from falling apart. And then very far out is a fuzzy, fuzzy, fuzzy ring, which is the E ring. And the E ring is made from the ice crystals that are being blown out by Enceladus. Okay, so these are the rings. Okay, so this Roche limit is somehow maybe number one, why the rings don't form a moon, but also where they come from, right? If something wandered too close, the tidal force would rip it apart. All righty. So does Jupiter have rings? You're supposed to know the answer, yes, it does. Okay, but what about that? How do we know the rings are there? And actually, it turns out we can't see them from Earth. The way that we see them actually is not, we can't see them from there. Sorry, we can't see them normally, but we do see them when we watch Jupiter very carefully. As it gets close to a star, the star will blink out before Jupiter gets there. And that is because the ring is blocking the light of the star. It's called an occultation. Okay. All right, so now we do notice there are some interesting spaces in the rings, and one of them is called the Encke division, and another is called the, forgot, what's the other one called? Cassini division, the Cassini division. And those are basically due to the some of the moons. Okay, so there's the shepherd moons and the F ring. And yeah, that's it. Oops, okay, that's it. I guess that's it. So please watch the little video clips. Okay, and we've got Uranus and Neptune, and these are gonna be pretty quick. We don't have a lot of detail. You can see they're kind of blue, right? One is more blue than the other. And why are they blue? You're actually supposed to know that. And the answer is the methane. Well, why? And it turns out they've got hydrogen, helium, and methane. And the methane, it turns out, absorbs the red color in sunlight and reflects the blue. And so we end up seeing a kind of blue hue to them. Okay. So Uranus and Neptune, Uranus is 19, call it 20 AUs. It has an orbital period of 84 years. And Neptune is 30 AUs and orbital period of 165. They have, instead of a regular rocky mantle, they have an icy mantle. And this is made of water ice, methane ice, and ammonia ice. Now these ones, actually, if you watch the Phil Plait video, you know that there's something else that's kind of interesting. In both Uranus and Neptune, we might expect to have not icebergs, but crystals of compounds made with carbon. And one compound that's made with carbon is diamond. So can you imagine diamond bergs floating underneath the atmosphere in this mantle layer somewhere of Uranus? So they have atmospheres 80% hydrogen, 18% helium. Okay, they've got methane clouds. They don't have as much ammonia, and they don't have the metallic hydrogen. Okay, they don't have it. So here's one of the biggest things you want to know. Uranus is tilted on its side and really dramatically, right? It's like 98 degrees, right? And as a result of that, it has what we call the most extreme weather. So instead of a tilt of 23.5 degrees that the Earth has, it's 98 degrees. It's like on its side, right? So this one, Uranus really, so Neptune is 28, Uranus is 98 degrees, okay? So Uranus really has extreme seasons because This hemisphere is facing the sun, but this one is not. So for quite a while, right, it's going to be facing like this. So you can actually see, where are we now? We're kind of in between here, right? Getting closer to 2020, so it's 13 years. Okay, we're kind of closer to this one. And so this would be Southern Hemisphere or Northern Hemisphere summer, whichever, I don't know which is which actually. I guess this is Northern. So Northern Hemisphere summer and is coming up. And it's going to last about 1/4 of the orbital period. So that would be 84 years. That'd be 21 years for each season, right? And we called it the most extreme seasons because of that. And we do see cloud formation changing as a result of the seasons, right? So we can see the clouds forming, more clouds in the winter, less clouds in the summer. Uranus, we're going to talk about only one moon for Uranus, and it has 27 in all, but we're going to look at this one right here. It's called Miranda. This is the innermost moon, and if you look at it, it's got a little bit weird. Actually, I don't have a picture showing you the spectroscopy, but if you take a very special picture of the surface with spectroscopy and you look at its material, you find that it's almost like two different moons. And actually, you can see, like, this one just looks so different from this, right? This looks like a regular moon. I kind of get it. What the heck is this stuff? And so the answer is, this is two bodies that very gently smushed together and formed one, right? And so the material on the lower part and the upper part, they're completely different. And so this is kind of evidence of what we talked about before. Remember, in the early solar system, if the protoplanets smash together, they break each other apart. If they just kind of nuzzle up against each other, they merge and form a single body. And that's how the planets must have formed. And so this is kind of an example for us of a moon-sized object that formed in that way. And so if that can happen, right, it gives us kind of credence to the concept that the planets could have formed that way as well. That's really like two different planets that merge together. So the only moon you need to know. And finally, let's go to Neptune. And again, I'm not going to talk much about Neptune. It's pretty much the same as Uranus, but I will tell you about this moon right here, Triton. This is a special moon, and it's very strange. First of all, it has a retrograde orbit. Remember, we talked about the irregular moons for Saturn. This one is irregular. This is captured. And where did it come from? This thing came from the Kuiper Belt. Okay, this thing came from the Kuiper Belt. One more time. Yes. And it also has geysers of water that are blown with nitrogen gas, right? So we see nitrogen gas and water jets shooting out of it. It's really weird. It's very strange. It's got geysers. Again, it's closer to Neptune, so that we think that probably it's going to be tidal heating that's causing this to happen, and not volcanoes, but geysers, cryovolcanoes. Okay. And how do we see the rings, right? We mentioned that Jupiter has rings, Uranus 11, Neptune has 5. The way that we find them is not directly, but the way that they occult stars, right? The light of the stars is blocked, which allows us to infer that they must be there, right? So the star just disappears, and the body of the planet hasn't gotten there yet. We can say that the ring is blocking the light of the stars. All right, and that is chapter 8. So please look at all the extra stuff. The extra stuff I have curated for you, and I think that it will enhance your understanding and hopefully your appreciation of the outer planets, the gas giants and the ice giants. And then take the quiz, and when you're ready, take your test. And if you have a need to see me, don't forget we have a tutor, but also most of you are not coming to my office hours. And so I think I'm going to be changing my office hours to be very flexible and for you. And what you're going to be doing is make an appointment with me, and I will meet with you anytime that you want. I mean, literally, unless I say, nope, I can't do that. But if you tell me a time you want to meet, please, let's try this out, because right now my office hours are not being utilized. Okay. And thank you so much for your attention.